So here the minimum distance required to stop a car moving at 35 miles per hour is 40 ft. So first of all, let's draw its figure. So we have a car moving with initial velocity, let's call it v1, and it can stop after distance x1. So question is, what is the minimum stopping distance for the same car moving at 70 miles per hour, assuming the same rate of acceleration? So basically here final velocity becomes 0, and we know that this car is decelerating with constant acceleration, deceleration. So we can say final velocity square equal to initial velocity square minus 2ax x1, let's say, for the first case, for the initial case. So final velocity becomes 0, initial velocity 35 miles per hour is given, v1 square minus 2ax1. So from here, from this equation, we can find its acceleration, magnitude of the acceleration, v1 square over 2x1. Now if we increase its velocity, let it be v3, and of course its stopping distance will be greater than x1, let it be x2, and the final velocity here becomes, let's call it v4, and it becomes 0, and we need to repeat the same calculation. Basically final velocity square equal to initial velocity square minus 2a, same acceleration but different distance. So here we use negative sign because of deceleration. So final velocity, of course, again becomes 0. v3 square is v3 is initial velocity for this case, which is 70 miles per hour, minus 2ax2. From here, acceleration equal to v3 square over 2x2. So we know that they have the same acceleration. So this acceleration equal to this acceleration. So v1 square equal to over 2x1 equal to v3 square over 2x2. From here x2, so we can cancel 2 here. x2 will be equal to v3 square over v1 square times x1. So v3 is here 70 miles per hour, v1 is 35 times x1, which is 40. So x2 will be equal to, it's just simple calculation, 70 square over 35 square equal to 4 times 40, which will 160 ft. So basically stopping distance increases by 4. If you increase initial velocity by 2, stopping distance increases by 4.